60 feet, no backbone, no skeleton, nothing we would traditionally call a weapon, just arms, fins, and a jaw that wore itself down, grinding through bone and shell year after year, in water so deep and cold that light has no business being there either. For 14 million years, this animal held the highest position in one of the most competitive marine ecosystems in Earth's history, sharing that ocean with mosasaurs, plesiosaurs, and sharks that would be considered giants by any modern measure. It outlasted most of them. It did this without a single hard structure in its body except for that beak, that one curved, dense, parrot-billed instrument of pressure that is, today, the only reason we know it existed at all. In April 2026, a research team out of Hokkaido University published a paper in the journal Science describing 27 fossilized cephalopod beaks recovered from ancient rock formations in Canada and Japan. The largest of those beaks was 1.5 times the size of the jaw of a modern giant squid, which itself represents the upper boundary of what invertebrate life has been capable of producing in the present age. When the team ran the scaling calculations, the same calculations used to estimate body size from beak proportion in living octopus species, the number they arrived at was 19 meters, 62 feet. An animal with no spine, no exoskeleton, and no precedent, sitting at the top of a Cretaceous food chain that included some of the most formidable vertebrate predators ever recorded in the fossil record. Scientists had been searching those rock formations for years. The fossils were always there. Nanaimoteuthis haggarti does not belong in the category of creatures we assumed dominated the ancient oceans. It does not belong in any tidy account of how predator ecology is supposed to work, or what soft-bodied life is structurally permitted to become. The evidence, however, is sitting in a laboratory in Hokkaido, and it does not particularly care what the assumed limits were. 60 feet of jaw-worn, fin-driven deep-water predator existed here, on this planet, in these oceans, and the work of understanding how begins now. To understand what Nanaimoteuthis haggarti was, you first have to understand what it was swimming in, because the late Cretaceous ocean was not a scaled-up version of the one that exists today. It was a fundamentally different body of water, running warmer, deeper in certain basins, and stacked with biomass at every level of the food chain in concentrations that the modern ocean simply does not replicate. The conditions that produced this animal were not accidental. They were cumulative, built over tens of millions of years of geological and ecological pressure that kept raising the ceiling on what was biologically achievable. 86 million years ago, when Nanaimoteuthis haggarti appears in the fossil record for the first time, the North Pacific was already occupied by predators that would register as extraordinary by any present-day standard. Mosasaurus hoffmanni reached 18 meters in length and fed on fish, cephalopods, and other marine reptiles. Plesiosaurs like Elasmosaurus extended beyond 10 meters, their long necks giving them a hunting geometry unlike anything alive today. These were not background creatures. They were the dominant vertebrate architecture of an ocean that had been selecting for size and lethality for a very long time. And they shared that water with ammonites 2 meters in diameter and cephalopods already approaching 12 meters in total length before Nanaimoteuthis reached its peak. What the fossil record shows across the breadth of the late Cretaceous is a consistent directional pressure toward gigantism in the ocean's invertebrate lineages. Not uniformly and not without exception, but clearly enough that Nanaimoteuthis haggarti does not appear as an anomaly when placed against its own geological moment. It appears as a product of it. The earlier species, Nanaimoteuthis gillespie, lived between 172 million years ago and reached somewhere between 3 and 8 meters, comparable to the largest living octopus today. Over the following millions of years, as ocean temperature, nutrient availability, and prey density continued to compound, the lineage scaled. By the time N. haggarti arrives, the size estimate nearly triples at its upper bound. This is not a creature that appeared suddenly. It was constructed by its environment across geological time, each generation inheriting an ocean that rewarded size, that sustained the caloric demands of a 60-foot soft-bodied predator, that offered prey dense and hard-shelled enough to explain the degree of wear found on those fossilized jaws. The late Cretaceous ocean did not produce Nanaimoteuthis haggarti despite its other giants. It produced it because of them, and because of everything else it had been quietly building toward for millions of years before the first beak hit the sediment. The beak is where the biology becomes difficult to dismiss, not the size estimates, which carry their own margins of uncertainty and have drawn legitimate scrutiny from researchers not involved in the original study, but the beak itself, The physical object, recovered from deep water sediment, measured, photographed, and compared against the jaws of every living cephalopod species with enough data to support a scaling model. The hood length of the largest Nanaimoteuthis haggarti specimen came in at 86.4 millimeters. The largest giant squid beak on record measures roughly half that. Whatever animal was behind this jaw, it was not operating at the edge of a known category. It had moved into territory that invertebrate biology, as we currently understand it, has no modern equivalent for. The first problem is structural. Soft-bodied animals face a constraint that vertebrates solved with bone hundreds of millions of years ago: the problem of supporting mass at scale. A skeleton does not just provide attachment points for muscle. It distributes load, transfers force, and allows a body to maintain coherent shape under the mechanical stresses of moving through water, seizing prey, and resisting the pressure of depth. Without one, an animal's own tissue becomes both the engine and the obstacle. The giant Pacific octopus, the largest living species, reaches a documented arm span of around 4 to 5 meters and a body mass that tops out well below 100 kilograms. Nanaimoteuthis haggarti, at its estimated size, would have required a solution to the mass problem that its living relatives have never needed to develop, because none of them ever got anywhere near large enough to encounter it. The solution, according to the fossil evidence and the biological inference built around it, came from 3 directions at once. The first was buoyancy. Water bears weight in a way air does not, and a deep ocean animal of sufficient density can offload a significant proportion of its structural burden onto the medium it lives in, using the pressure gradient of the water column as a passive support system that no land-based body plan has access to. The second was the fins. Nanaimoteuthis belonged to the Cretaceous, the finned octopuses, a group still present in today's deep ocean in much smaller form, recognizable by the ear-like fins on their mantles that allow them to maneuver without the energetically expensive jet propulsion that other cephalopods rely on. At 60 feet, jet propulsion is not a viable locomotion strategy. The fins made sustained movement through deep water mechanically possible in a way that no other octopus body plan could have supported at that scale. The third direction was the jaw itself, and this is where the evidence stops being inferential and becomes forensic. Wear patterns on the recovered beaks show consistent, heavy abrasion concentrated in ways that researchers were able to rule out as environmental. All specimens came from deep, low-energy sediment conditions where coastal abrasion is not a factor. The wear came from use, from the repeated mechanical compression of hard materials, shells, bones, the calcified structures of prey animals substantial enough to grind down a chitinous beak over the course of a lifetime. Several specimens show jaw loss approaching 10% of total hood length, which represents an extraordinary degree of accumulated contact force across an animal's lifespan. One additional detail in the wear pattern carries its own implication. The abrasion is asymmetric, more pronounced on one side than the other, in a pattern consistent with lateralized feeding behavior. A preferred side, the way a person is right or left-handed, which in vertebrate neuroscience is understood as a marker of hemispheric brain specialization. Lateralization in an invertebrate of this size in the Cretaceous is not a detail the paper foregrounds aggressively. It sits in the data, noted and measured, available to anyone reading carefully. An animal 60 feet long, hunting hard-shelled prey in deep water, with a brain complex enough to develop a dominant side. Built without a single bone in its body, out of nothing but soft tissue, fins, and that jaw. The soft tissue is gone. The jaw remained. And the jaw tells us what it was doing. Not in metaphor, not in inference drawn from distant analogy, but in the direct physical record of an animal's feeding behavior preserved across millions of years of compression and sediment. A record specific enough that researchers could distinguish between wear caused by environment and wear caused by prey, specific enough to identify lateralization, specific enough to place this animal not at the margins of the late Cretaceous food web, but somewhere near its center. The question the 2026 paper raises, carefully with the measured language of peer-reviewed science, is whether Nanaimoteuthis haggarti was not merely a large predator operating in a rich ecosystem, but a genuine apex predator in the technical sense. An animal at the top of a food chain with no natural predator of its own and a functional role in regulating the populations of everything below it. That claim requires scrutiny, and the researchers apply it themselves. Jakob Winther, a paleontologist who reviewed the study, noted that the fossil does not constitute direct evidence of Nanaimoteuthis, thus taking down large marine reptiles, and that the energetic logic of hunting prey that large, the time required to subdue, kill, and ingest an animal of comparable or greater mass, may not have matched the caloric return that smaller, more accessible prey could provide in greater volume. An animal this size has enormous energetic demands, and those demands can be met through different hunting strategies. Frequency of smaller kills and rarity of larger ones is a pattern seen across multiple apex predators in the modern ocean, including species that are perfectly capable of taking large prey but do so selectively and opportunistically rather than as a dietary staple. What the jawware establishes beyond reasonable dispute is that Nanaimoteuthis haggarti was feeding regularly on animals with hard skeletal structures. Creatures armored enough, shelled enough, or boned enough to grind down a beak over years of repeated contact. The Cretaceous North Pacific offered a wide menu of candidates: large fish, ammonites with shells approaching 2 meters in diameter, other cephalopods, and marine reptiles that, whatever their size advantage in length, would have been vulnerable to an animal capable of applying the kind of compression force that level of jawware implies. Whether or not it hunted mosasaurs as a primary prey item, it occupied an ecological position that vertebrate predators also occupied, and it did so at a body size that placed it within the same size class as several of them. This is the claim that restructures the broader picture. For the better part of a century, the working model of Cretaceous marine ecology positioned vertebrates, sharks, mosasaurs, plesiosaurs, as the uncontested architects of the food web's upper tier, with invertebrates filling subordinate roles regardless of their size. Nanaimoteuthis haggarti does not fit that model. Through what the study's authors describe as convergent evolution, cephalopods and vertebrates arrived independently at the same ecological solution: a large-bodied, jaw-bearing, active predator capable of taking hard-shelled or hard-boned prey, operating without an exoskeleton, in direct competition with the vertebrate lineages that were doing the same thing in the same water at the same time. Two entirely separate branches of animal life, separated by hundreds of millions of years of divergent evolution, producing the same functional predator from completely different biological materials. Vertebrates built their version with bone. Nanaimoteuthis built its version with fins, soft tissue, and a beak that ground itself down against the evidence of what it was eating. Both versions worked. Both held the top of the food chain in the oceans they inhabited, and for the 14 million years that Nanaimoteuthis haggarti persisted in the fossil record, neither version appears to have eliminated the other. They shared the apex. They competed for it, endured alongside each other, and together defined what the ceiling of Cretaceous marine predation actually looked like, which was nothing like what we assumed before the jaw came out of the rock. Before the jaw came out of the rock, the assumption was clean and uncomplicated. Vertebrates dominated ancient marine ecosystems, invertebrates filled the spaces between them, and the fossil record, incomplete as it always is, broadly supported that picture. The assumption was not unreasonable. It was built from evidence available at the time, applied carefully by serious researchers across decades of accumulated work. The problem was not the methodology. The problem was that the most important fossil in the argument was still inside a piece of Cretaceous sediment in a formation on Vancouver Island, and nobody had yet found the specimen large enough to force a revision. Ikegami and colleagues found it: 27 beaks recovered from rock formations in Canada and Japan, examined against the proportional scaling data of every living octopus species with sufficient jaw-to-body measurement records to support the calculation. The largest specimen measured 86.4 millimeters at the hood, 1.5 times the size of the largest giant squid beak in the comparative dataset. The body size estimate that followed from that measurement sat between 6.5 and 19 meters, with the lower bound alone sufficient to place Nanaimoteuthis haggarti among the largest invertebrates ever documented from the fossil record. Not the largest animal in the Cretaceous ocean, not the most terrifying thing in that water by every possible measure, but an invertebrate, built entirely from soft tissue, holding a position in the food web that the previous century of paleontology had reserved exclusively for animals with spines. Some researchers remain cautious about the upper end of the size range, and that caution is scientifically legitimate. Scaling cephalopod body dimensions from beak proportions is not a direct measurement. It is a model, dependent on the assumption that the relationships between jaw size and body size in living species held consistently in extinct ones, across a body plan that had no modern equivalent at the scale being estimated. The model may be right, it may be conservative. The honest answer is that the soft tissue is gone, and soft tissue does not fossilize, and the ceiling of what Nanaimoteuthis haggarti actually achieved in life may be a number the fossil record is structurally incapable of confirming with precision. What the fossil record can confirm, What the jaw confirms, sitting in a laboratory in Hokkaido with its asymmetric wear and its ground-down hood and its measurement of 86.4 millimeters that nobody who has seen it disputes, is that something was here. Something enormous, soft-bodied, lateralized, and capable of sustained predatory force occupied the North Pacific for 14 million years, alongside the vertebrate giants that we have spent a century treating as the only animals that mattered in that ocean. The jaw is the proof. The jaw is also the limit of what we currently know. Both of those facts belong in the same sentence, and the science is large enough to hold them.